I want to start this afternoon's session with a session about how we use MATLAB together with C and C++ for signal processing algorithm development. My name is Graham Reith. I work with the MathWorks as an industry manager for the communications, electronics and semiconductor industry across Europe and China. So I'm very glad to be here in Beijing. So let's have a look at signal processing algorithm development with C and C++. Typically, we start with a specification, an idea of what we're going to develop. We then go into our development process within C and C++, and we may call on specialized library routines in C to help us. We may also develop library routines that we can reuse and reshare for different projects. As we develop our algorithms, of course, we need to test them and debug them and make sure that they're free of errors. And once we're happy with that, we can then deploy onto our chosen system. If it's an embedded system or a desktop application, we need to make sure we can take it there. And this is an iterative process. Through each of these stages, we may need to go back earlier to fix problems in the algorithm. So I think this is a fairly normal software development cycle. Okay, so I'd like to look at how that C and C++ development process can be improved with better use of MATLAB's capabilities for data analysis and visualization, the way we develop algorithms, and also generate code and deploy those algorithms in that process. So as I go through this presentation, I'm going to split this design flow up into three different stages. We're going to look at how MATLAB can get added to the development flow for algorithm development, for the test and verification, and for the implementation and deployment. And in this overview, I'm going to provide a number of examples to show these capabilities. Examples from communications, from computer vision, and from signal processing applications. So let's start with the test and verification part of this flow and how we can use MATLAB for that. The example I'm going to use is an example from communications. I'm going to look at how we can use a project in C that does a Bluetooth simulation and how we can use MATLAB to enhance that process for better data analysis and visualization. Okay, so let me start by switching over to Visual Studio. So this is a project inside Microsoft Visual Studio that does some processing for a Bluetooth simulation. So this file, it's publicly available on the internet. It came from the National Institute of Standards and Technology over in the United States. And it does a simulation of Bluetooth together with wireless LAN. So when I build a project like this, then I get an executable file that I can then run. So let's go ahead and run that executable file. To run this executable file, I've gone to the command line and I can call that, it's called btint. I can pass in some parameters like EBN node, the signal to noise ratio, and let's say that that's there at 40 dB. If I execute that code, I get some text displayed back to me to give me those results. I have some parameters that tell me how the simulation ran, and I have my bit error rate. Here it says it's 0. 40 dBs of signal to noise ratio, that's reasonable. If I ran this with a higher or lower signal to noise ratio, say just at 3 dB, then you can see our bit error rate is down at 0.2. So we have quite a lot of errors happening at that level. So what happens if I want to find out more about what's happening in my execution? So one way is I can go to Visual Studio and I can debug in Visual Studio and use the watch window to look at variables. Another commonly used method is to have a a hash defined to write to file, to dump data out of the simulation and put that to a file. So I could specify a flag here to write to the file, import the data into MATLAB and visualize it in MATLAB. So let's go and do that. So in MATLAB, when I ran this application before, I had some data files created by the application, so the imaginary and real parts of this data. As we know in MATLAB, we can right-click, we can import this data. So let's import the imaginary data in. I'm going to use the import wizard to do this. Let's call this iData and import that selection. That's that one done, and let's go to the real. So let's choose to import that data. Let's call that the R data. Import that. And then that allows me to then say that my data is the real data plus I times the I data, and we could then plot that data inside MATLAB. So I can see I have a line. These represent points on the unit circle. Let's just show that a bit better. So I can see the different sample points from my signal by plotting in MATLAB. And this is quite typical. What I'd like to show you is how we can do better than this by using MATLAB together with C. Okay, so let's go back to my Visual Studio project. And I'm going to change a parameter here to set this to be mode 1. If I go to my main file and I have a look at where mode 1 is defined, let's go back to the start, we can see that rather than including data for the write to file options to do file access, we are now including something called engine.h. So this is a call to the MATLAB engine so that we can communicate with MATLAB directly from Visual Studio, or from the executing C code. If I have a look a little bit further down, then when mode is 1, we open the engine. That means we open the access to MATLAB. And then the next time we create some data in the MATLAB format, and then we populate that with the right data that we want to have sent to MATLAB. Finally, we pass the data to MATLAB, and then we can call MATLAB commands from our compiled C code that's executing. We can invoke MATLAB, call MATLAB commands, so I can see and visualize and understand what is going on. So let's go ahead and just recompile this project. Okay, so I have recompiled my project, and now if I go to my command line, I can re-execute my call to my executable that's been rebuilt. See, it's sending data to MATLAB. And if I have a look inside MATLAB, I now have a plot that's been created in MATLAB that is receiving data from my C code application, and I can see what's going on. So I can see all this data stream of information coming from my C code, and if I work in communication systems, I can look at that graph and I can understand what's going on. I can recognize the modulation scheme, and I can verify that my code is doing the right thing. If there's a problem, this can help me understand what the problem is, and then help me understand how I can fix it. So let me return to my slides. So what we saw in that example was how we could use MATLAB together with C to help us debug or investigate what was going on with that executing C code. How we did that: we added header files and libraries to the project. We packaged the data into the MX array in a format that MATLAB expects, and we used these engine routines in order to send the data to MATLAB perform the calculations in MATLAB, and visualize some data in MATLAB. There's a C++ example available online at that link. So to summarize how we call MATLAB from other languages, that engine interface can be used with C and C++ as well as Fortran code. And MATLAB can be called as an automation server if you're developing COM or .NET applications as well. And you can also do this the other way around. So rather than have other languages call MATLAB, have MATLAB call other languages. So C, C++, Fortran, COM, .NET, Java, all of these languages can be called from the MATLAB interface. As an example, if you have a C shared library, something like a DLL, then you can use the load library function along with the header file to bring that function into MATLAB so that you can call that code. So looking on, do you need access to good quality signal processing libraries when you're developing your signal processing applications in your C projects? So what we have seen with the engine interface enables you to call functions inside MATLAB as you develop your C code. But it also takes me to the next section where I'm going to look at the development of algorithms directly inside MATLAB. Functions for filter design, different spectral analysis functions, functions for waveform pulse generation are all available. So in this next section, we're going to focus on that algorithm development portion and look at how MATLAB differs from C and C++ as a development with which to develop your algorithms. So I'm going to start off by looking at that problem of filter design. So I'm going to look at how MATLAB provides tools for us with which we can design and develop our algorithms. So let me change to MATLAB. And inside MATLAB, you'll see that now in recent releases of MATLAB, along in the tool strip, we have a range of MATLAB apps that are available for different functions. As part of the signal processing toolbox, there's an app for digital filter design. So if I fire up that filter design and analysis app, then you can also call this from the command line by typing FDA tool. Then within this, I can use this to design a filter to meet particular constraints up here on the right. I can choose a different response type I might be interested in between low pass, high pass, band pass types of filters. And on the right here, specify the different frequency and magnitude specifications I want for my filter. The pass band frequencies, the stop band frequencies, how much attenuation I want, and so on. On the left side, I can also then choose the method with which I design my filters. So finite impulse response and infinite impulse response filters, a range of different functions are available with which I can go ahead and design a filter. Having designed my filter, there's then various bits of analysis that I could do. So I could look at the phase response. As this is an FIR filter, this is a linear phase response, as we would expect. I could look at group delay. Again, this is flat because the phase response is linear. Impulse response, the poles and zeros. Look at the filter coefficients. All the kinds of analysis I might want to do when designing these kinds of filters for signal processing is available directly. What I can then do, thinking about using this filter, is I can then take this filter and I can export it. I can either export it just as the coefficients, or I can generate some equivalent MATLAB code to design that filter, create a filter design function directly in MATLAB. As we're talking about C programming here, one particular thing to highlight is that I could take these coefficients directly and put them into a C header file that I could then call within my project. So that could be another way of going from here directly into a C application. Rather than looking at just a filter, I want to go ahead and look at a slightly more complex design. If I go back to my slides for a moment, what I want to look at is an application for real-time filter tuning. So a filter where I might adjust some parameters during execution and change the filter characteristics while my application is running. This is the sort of thing you might have on a stereo system, like an audio equalizer, where you change some parameters and the filter that are applied actually changes and you can hear the difference in the sound to do that. So if I was responsible for designing that algorithm, I'm going to look at how we might simulate that algorithm inside the MATLAB environment. Let me go back to MATLAB, and I'm going to use one of these shortcuts in order to change to that particular project and open up this example. So here I have some code that runs my example. I will look at the code in a moment. But first of all, I'm just going to run this example and we can see what it does. Let's give this a second to start up. Okay, so we have my system running. What we have in the purple line here, and there's a yellow line underneath, represents my audio spectrum, and what we have in the blue line represents white noise. So I can have a look at my filter characteristic while it's running. If I look at this application while it's running, then one thing I can do is I can interact with this application. So I have a user interface here on the right that I can adjust. I can see from the blue line that I'm affecting the shape of my filter that's being applied, and I can move the center frequency here with this line over here. And whilst my filter is running, we can also see on this spectrum analyzer display, I can see the characteristics of this filter updating as I change my application. If I want some more analysis than this, I can open up this peak finder utility as part of this spectrum analysis display here. Let me just change the channel. So channel 1 and 2 are left and right, channel 3 is the white noise. And I can see here I've got the peak values displayed here. Let's sort this by value to pick up the highest peak. So we can see here some real-time display of the particular frequencies we are looking at through my scope. And as I adjust my application, let's move this parameter over here, you can see we can get some feedback of where that peak of that filter function is as we have this live streaming application. So let's have a little look at this code just as a very quick overview. What I can see if I look at this code is I have a number of different components from the DSP system toolbox that are created at the start. An audio file reader to read in this MP3 file I was using as the audio. My tunable bandpass filter algorithm, an audio player, a file writer, a spectrum analyzer, we saw the spectrum analyzer display, and some code for the user interface control, the sliders I was using to control the filter in my application. I then have a single loop that does the processing on that data, that gets the data, next block of data from the file, passes it through the filter, passes it to the spectrum analyzer. When that block is finished, goes and gets the next block of data from the file. So this is very representative of how real signal processing applications get implemented. It's a stream of data. You get some data, you process it, you pass it on to something else. You get the next block of data, you process it, you pass it on to something else. And the loop continues until you run out of data. So within MATLAB, I can very quickly create these streaming applications, in this case using functions from the DSP system toolbox. And it's very representative of what my application is going to do if it was running in real time. And if I look at the code here, what I have is I have 76 lines of code. That includes all the comments and the spaces in this file. So really I have quite a compact set of code to enable me to develop that streaming application that you just saw. Okay, so let me go back to my presentation at this point. So here in this application we saw how we can develop algorithms with MATLAB and saw some of how it is different from how you might develop applications in C. Particularly whether you're writing scripts or functions or you're making use of these system objects from the system toolboxes, you have a very productive environment integrated with visualization routines that has the capabilities for real-time streaming of data, and that really helps you develop your applications iteratively and to debug them and validate that the algorithm meets the specification and do that very quickly. So finally, particularly when you are developing applications that are intended for real-time deployment, this streaming approach, being able to use that streaming structure in your code really helps prepare your application for that deployment phase. So let's just summarize what we saw there with signal processing applications in MATLAB. So what I showed was a signal processing application, doing some audio processing, designing a filter for it, and making use of those functions to analyze what was going on. These capabilities also are there within these system toolboxes for wireless communication systems, computer vision systems, phased array, radar systems. All these capabilities are things that you can draw on in order to build up the algorithm models for the applications that you develop. Other presentations will go into more detail in some of these areas. The point is that these are ready to use algorithm libraries, and they enable the development of real-time signal processing applications for your particular design problems. Okay, and one example of where a local customer here in Beijing is making very good use of these tools is the example of Docomo. So here they are using MATLAB to aid in the development of mobile communications technology for next generation mobile standards. And I chose this example because I particularly like some of the things that they said that is very relevant to this topic. If I quote from the lead research engineer's quote on the right, "With MATLAB, we spend less time coding and more time developing innovative mobile communications algorithms." So that means they spend more time doing productive work on their research and on their development rather than coding in order to do that. Also, what they go on to say is that when they do this, through the use of MATLAB, they are able to very easily access high-performance computing technology to help them in their work. So here they make use of the parallel computing tools to be able to take their simulations and deploy them to clusters through the parallel computing toolbox. So that's a really important point. If I think about developing applications in C and C++, within MATLAB, you've got ready access through the parallel computing tools to access high-performance computing technology, whether that's multiple cores on your desktop, whether that's access to a computer cluster, whether it's access to a GPU that's installed on your machine. We've done a lot of the work to make accessing that high-performance computing technology easy. So if you're developing in MATLAB, that's just available to you with that toolbox. Okay, so I'd now like to take a look at the next section. So let's say we've developed our signal processing application in MATLAB. The question is, do we actually need C for that application? Why do we need it? Well, typically, we may very well need C for the application. particularly if we are integrating our code with external C projects and it doesn't want to be a dependence on a MATLAB license. We might be developing embedded applications to run on embedded processors, or we may have, for example, it's very common to have standalone C simulators that you need to integrate your algorithms with. So let me now move on to the last section, where I'm going to talk about the capabilities of the tools for implementation and deployment. So in order to do that, I'm going to look at an example which does some video processing of some data. And in this case, I'm going to be looking at how we can generate C from the MATLAB environment and integrate it with a C project. So the application I'm looking at here, it's some video processing from a vehicle with a camera on the vehicle, where it's looking to identify the road markings to aid the driver driving that vehicle. So this is part of an automotive safety application, where your feedback on when the vehicle is moving from one lane to another without indicating, by alerting the driver that this is happening, it can be useful to maybe wake them up if they have fallen asleep. So this is the kind of application that is being developed for automotive safety applications. So let me change to MATLAB. Let me clear up my screen a little bit. And let me open up this project. So I'm just going to run the code here so you can see what this does. We're going to take in some video from file and we're going to stream it through my application, visualize the results on this. I'm not going to go into the details of the algorithm itself. So here you can see on the screen the processing of the data. I know the traffic here is very different to the traffic I see outside in Beijing. But the idea on this graph is you get to see the results of where the lanes have been identified, marked up with these red lines. And it gives me that feedback to verify that my algorithm is working. What I'm now going to do is I'm going to generate code for that algorithm and integrate it with my C project. So in order to do that, what I would do, I'm going to open up my project where I've already populated it, but we can show you the process. So my project is a code generation project, and I have put in my entry point, which is my lane marking algorithm, and I've then specified the size of the input into this algorithm. So because I'm generating C, I can't make use of MATLAB's variable data types, or I might not want to use MATLAB's variable data types in quite the same way. So I can specify the dimensions of the input inside here. And in the build section, I can then choose what I want to do. In this case, I could create a MEX function, a static library, a DLL, or even package things up into an executable directly from here. I'm just going to generate the code, and I could then click on build and generate code for my lane marking algorithm. So this is now invoking MATLAB Coder in order to translate my MATLAB code into C so that I can use it in my C project without needing MATLAB. Okay, so it's just taking a little while to complete that. So what I'm going to do actually is I'm going to change to my Visual Studio project. I'm going to actually call some code which was generated from this before. And here we can see the C code that I have generated previously. So if I look in the project over here on the right, you can see all these C files that have been generated for my lane marking algorithm. Okay, there's the report that's been generated by MATLAB. We could look at the code in here as an alternative and see where it came from and look to seek to improve it. With this running directly inside my algorithm, inside my C project, if I go ahead and build my project, let's just click on F7 to build my project. Everything was up to date already. Then if I choose to run this, when I run my project, it's now going to run my C code for that along with all the other files that I might have written myself to handle the inputs and outputs from my data file. So, to summarize, I'd like to actually choose the opportunity here to summarize a few differences between two of our deployment products. So one, the MATLAB coder, and the other, the MATLAB compiler, which you may also have heard about. So from MATLAB, within MATLAB, we develop applications that consist of visualization, of algorithms, of graphical user interfaces, maybe even interfaces to external equipment. If I take just the algorithm, the mathematical algorithm, then I can use MATLAB coder to translate that MATLAB algorithm into C code. That gives me ANSI C code, the raw source, that I can then package up into DLLs, libraries, and executables. If I want to deploy more than just the algorithm, but actually I want to deploy the visualization, the user interfaces, as well as the algorithm, and interfaces to hardware, data acquisition, instruments, things like that, then it's possible to do that. But I use the MATLAB compiler to do that. So that enables me to deploy a lot more things out of MATLAB, almost everything out of MATLAB. Whilst it gives me an executable, it doesn't give me C code. It makes use of something called the MATLAB compiler runtime in order to execute it, so this person does not need a MATLAB license to run the application, but it is limited then to desktop applications, and if I want the source code, the MATLAB coder is the thing I need to do for my algorithm. Otherwise, for desktop deployment, it's the MATLAB compiler. Okay, so to summarize what I have tried to cover in this presentation, it's about how you can extend what you do within C and C++ at the moment, if you're using C and C++ as your primary development language, and how MATLAB can extend that for data visualization, using the engine interface and to visualize what is going on, to help you with algorithm development, using the built-in tools for developing signal processing algorithms and the libraries, and some of the methods for generating C code directly from the algorithms that you have developed inside MATLAB, so that you can package them in your C or C++ application or interface them with your other desktop applications. And that's why we feel that MATLAB together with C and C++, that makes a really great combination for developing your applications, your signal processing applications. Okay, so that brings me to the end of my talk. I'm very happy to take any questions if anybody has any.
第一个问题就是刚才我看说，你运行一个程序，把结果输出到 MATLAB 上，可以实时的画图分析。这种调用 MATLAB 的方式可以是远程的吗？比如说一台 PC 上的东西在另一台 PC 的 MATLAB 上画，或者是手机里的程序在 MATLAB 上画，这个可以远程访问吗？
Okay, so it would be possible to take MATLAB and listen to TCP/IP, so Ethernet packets, providing your application can transmit data over the network. So you can build applications which send data over the network, and MATLAB can then visualize that data. You do it in a bit of a different way to what I showed you today, but it is possible to do that.
我想问一下，就是那个 MATLAB 里边有好多专门的那个函数库，就是 FFT 啊，说小波变换这些专门的函数，它转换到 C 的话是怎么转换？有没有方法？
So certainly the FFT can be translated to C code. So a lot of the core mathematical capability inside MATLAB, quite a bit of the signal processing capability, and also some of the capabilities in other toolboxes. You can translate them to C. So, yeah, a lot of the fundamental maths is there. If you have particular functions that you're wondering about, let us know and we can answer that offline.
我的问题是，就是对于 C++ 来说，C++，那么和 C 的这个运作方式，就是它的这个功能是完全一样的吗？还是说有一些特殊的那个操作或者要求？
So it's the same as what you see here. When we generate code, we can generate encapsulated C++, so you can package it easily into your C++ project. The core of the algorithm remains C.
如果我想把一个 MATLAB 的工程或者函数转换 C 的时候，就是对这 MATLAB 的编程有什么要求没有？还是说就是我 MATLAB 只要能跑得通，我那个转程是肯定能编译通过的？
So there is some tools to help you. I haven't had the time to go into the details of those tools to help you. One particular tool is something called the screener. So for example, if I have some code that I'm interested in taking to a function, so this lane marking algorithm, then there is a screener that I can run that will check my code to see if it is suitable for translation to C. So if I do that, I get a report that shows me the things that I might need to change in my code. If you think, as you write your code, if you think like a C programmer and structure your code well, you should have no problems. So you see, you get this code generation readiness score to tell me that maybe there's some minor functions, I'm not quite sure why that's coming up, and quite exactly where the changes in your algorithm are required. For this version of the algorithm, it's telling me that this function is not supported, for instance. I'm not quite sure why, I must be in the wrong directory. But the idea is there that this gives you feedback in how you can then adjust your code to make sure it is compatible.